Circle the best choice for each row, and we'll be ready to go. How much more time we need? Everybody got your answers picked? Let's see how you did. You guys want to know the answers? You guys, the answer to the first question was boar. Your answer to the second question was arrow. Your answer to the third question was egg. Your answer to the fourth question is ascot. Raise your hand if you got all four correct. It's about what I anticipated. Anybody get 3 correct? 2, 1, none. Okay. All right. So obviously, you guys did not know the answer to these questions, right? Neither did I, because I used a random digit generator to decide what the answers were, okay? So, are you with me that for each of these questions, you just made a random guess? Okay, so, how many possible outcomes? So we had 4, in this case, we had 4 trials. Each question is essentially a trial. Everybody good? And within those 4 trials, what were your possible outcomes? You either got the answer correct or you didn't. Okay, so we might see 5 choices, and those 5 choices make us think there might be 5 outcomes. But in reality, you guys, in fact, I said A is for arrow, and somebody in the back went, let's go, right? And that was because they got it correct, yes? So the outcome was actually correct or incorrect. Is everybody good? All right, so knowing that, couldn't we build a tree diagram of these, yes? All right, so this first set of branches is question number 1, and our outcome is correct or incorrect. And then we can keep rolling, right? All right, now, the tree diagrams we did with the coins, we never worried about probabilities because for a coin toss, heads, tails were equally likely. But in this particular problem or setting, is the probability of correct and incorrect the same? No. So just because we have 2 possible outcomes doesn't mean those 2 outcomes are equally likely. So what we're going to do is put the probability of each branch. What is the probability that you got the first question correct? 1 out of 5, right? 5 possible answer choices you were picking, only one of them was a correct answer. So are we comfortable calling that 0.2, 20%? Okay. Now, so this next piece, what about the next question? What's the probability you got the second question right?
Still 0.2.
And all the way through, we have the same probabilities. How are we feeling so far? All right. The next thing I'd like us to do, so if you think about it, this bottom branch represents all the possible ways you could answer these questions. Right? So when I look at this C right here, this C right here actually goes with all the C's leading up to it, yeah? Is everybody with me? So at the end of each branch, let's go ahead and count how many correct we got at the end of each branch, okay? All right, so for that first one, I'm going to go C, 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 C. That is how many correct? 4. What about the next branch? Well, that would be C, 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 I. So that would be 3 correct. And then C, C, I, C. You guys catch my drift? So let's go ahead and write in for each of these how many correct at the end of each tree. How are we doing? Okay, so is anybody shocked to see that the numbers range anywhere from 0 to 4? That you can get anywhere from 0 to 4 correct. That feels pretty natural, doesn't it? Okay, so my table of possible results here. The possible scores I could get on this quiz range anywhere from 0 to 4. Okay. All right. So the next thing I want us to do, I'm going to highlight all the branches of getting 3 correct. And there's 4 of them, yeah? And I very intentionally highlighted the probabilities of this. Okay, you guys, that first branch I highlighted from, I have a 0.2, a 0.2, a 0.2, and a 0.8. So 3 0.2s and 1.8. Why do I have 4 different probabilities being multiplied? Because I had 4 different trials. So 1 probability for each trial. If I do that next branch over, 0.2, 0.2, 0.8, and 0.2. Yes? And then the next one, 0.2, 0.8, 0.2, 0.2. And then 0.8, 0.2, 0.2, 0.2. What do you notice about all of those probabilities? These are all 0.2 to the third times 0.8. Every single one of them. And that, in our heads, are you guys with me that getting 3 correct also means you got 1 wrong? So for each one of these, we multiplied by 0.2 3 times. And then 0.8 once, 3 correct, 1 incorrect. Is this okay? Yeah. And so if I want to know what is the probability that somebody got 3 correct, I could say, well, in 4 different ways, we had 0.2 to the third and 0.8. We can figure out what that is then. What is the probability we get 3 correct? 0.026, great. Now, what about getting 4 correct? How many ways did that happen? Once. And so if I have 4 correct, how many 0.2s should I have? 4. How many 0.8s should I have? 0. 0.002. How many ways could I get 0 correct? Just one. How many 0.2s would I have if I've got no correct answers? 0. How many 0.8s? 4. Likewise, how many ways can I get 1 correct? Hopefully 4. Okay. How many 0.2s should I have? 1. Because getting 1 correct is one probability of success. And how many 0.8s should I have?
3.
That also works out to be 0.41. And then there are 6 different ways to get 2 correct. So 2 0.2s and 2 0.8s. I'm sorry?
Is it 0.154?
And what do those all eventually add up to if we don't account for rounding? 1. Okay. So yesterday we talked about tables where I gave you a table like this. We found the mean, we found the standard deviation, all that kind of stuff. Okay? Where this shifts is now, we're not going to keep writing out these tables, because what if I had given you a 15 question quiz? Are we doing this process to do a 15 question quiz? We could. I don't know that I have enough board space to draw that tree diagram, yeah? But can we at least envision kind of in our heads that that tree diagram exists, and that there's definitely a set pattern here that is very predictable? Almost like we could call that set pattern programmable into a device that's really good at doing quick calculations. Is everybody with me? Okay. Now, one more thing. I know some of you guys look at my stature and think, man, Miss Meister never played basketball. That's not true. I did play basketball. I had one job on the basketball team, and I'll tell you what it wasn't. That's very representative of my shooting skills on the basketball team. If I shot the ball, the coach pulled me out of the game and said, My job was to break the press, by the way, and to run the top of the 1-3-1, and to run the top of a 2-3 zone. I had low center of gravity, and I could dribble. And I had a lot of endurance, so I would also be in charge of pressing and breaking the press, depending on if we were on offense or defense. So you guys, what if, and 20% is definitely optimistic at my shooting ability, okay? If I asked you guys to create a tree diagram for me taking 4 shots, and my probability of making any one of those is 20%, I'm a 20% shooter, which again, very optimistic. Are you with me that this tree diagram would look identical? And therefore, this table would be identical, because it would still be 20/80, right? We'd still have 4 sets, okay? And so what we can do is we can define that scenario, that context, as a new kind of variable called a binomial variable. And this particular binomial was n equals 4 with p equaling 0.2. And anything where we have 4 trials with a 20% probability of success can get modeled by this table. And it's always going to be the same, because that tree diagram is going to always work out the same way. Okay? And it turns out that there's big fancy formulas that we kind of were starting to use here that are pre-programmed in your calculator. So I don't want you to worry about calculating this, but we do want to make sure we can use our calculator. And it doesn't apply, like, I can't use this if certain rules aren't in place. Like, these patterns existed because of certain things. For example, if I took 5 shots, 6 shots, or if I gave you 5 or 6 questions, I wouldn't have 4 probabilities here. I would have 6. Right? So the rules would change. And all of a sudden, the number of ways stuff can happen changes. Okay. So the first thing that makes, and then the other thing that we need to think through is this particular tree diagram. Each branch only had 2 options. Okay? So the rules we're about to learn only apply when certain conditions are met. Okay? So something is considered binomial. First thing for binomial is that you have a set number of what we call binary trials. Binary meaning you can define the outcome as success or failure. So we have to know how many times how many questions are on the quiz, or how many times Ms. Meister is taking a shot. Is everybody okay? All right, the next thing. Each trial needs the same probability of success. Now, can we see in these formulas what would happen if, like, question 2 had only 4 options, then the point 2 and the new probability of success wouldn't match? Is everybody with me? Okay, so, and then the last thing is our unknown quantity, the thing we're attaching our probability to, is a number of successes. So for each one of you, what we didn't know about you was how many you got correct. Is everybody good? All right, let's go ahead and... I could ask you, what is the probability that x is equal to 2? What's the probability somebody gets 2 correct? And can we use this table to get there? What is it? 1.1. What if I asked you the probability x is less than or equal to 1? Can we do that? What would we do? So less than or equal to 1 would be these, yeah? That's essentially describing that part of the table. So 0.82, adding together those two, the 0.41 and the 0.41. Are we good? Page? All right, now, some symbols that we're going to be using quite a bit, so I just want to real quick make sure we know what they are. N is going to be our number of trials. P is going to be our probability of success. Q is our probability of failure. And X is our number of successes. All right. And the way we're going to figure out probabilities is we're going to find something like, find the probability that X is equal to some number. Okay? So if I go back to the previous page real quick, I'll give you guys a second to get this down. All right. So your calculator is pre-programmed with 2 things. One is called binom PDF. One is binom CDF. I will show you where they are in just a second. The way you decide is if you're trying to find the probability that X is equal to something, the binom PDF will give you that answer. If you want to find the probability X is less than or equal to something, binom CDF will give you that answer. I got a better visual. I think it's going to be better. Okay, so first thing we want to do, here's a setting. I want to know, can we use this binomial model to get there? Okay? So consider I'm rolling a dice 20 times. X is the number of times we roll a 3. All right. Do I have a set number of repeated trials? What is each trial? It is rolling a dice, right? All right, so I have a set number of trials, that is 20. And what are we measuring? Like I roll the dice and I'm saying, did I get a 3 or did I not get a 3? So those are binary, 2 possible options. Everybody good? All right, do we have the same probability of success each time?
Yeah.
What is that probability?
1.6 repeating.
1/6, or if you put that as 0.167, whatever. Both are fine with me. Okay. So once I know something's binomial, now say, what is the probability I get exactly 4 3s? Everybody good? All right. Would you guys like to draw out this tree diagram for 20 trials? No. Yeah, me neither. Okay, so let me show you where to find the binomial PDF and CDF. Okay, we're going to use a menu of the calculator you have not used yet. Okay, sometimes we call the binomial a known and predictable probability distribution. So you're going to hear me say something is binomially distributed. So I want you guys to stare at your calculator. And if you stare hard enough, if you look above the VARS button, which is right next to the clear button, you'll see it says blue and then distribution. Yes? So hit second and then distribution, please. And you see a list of a lot of things. Yes? Mm-hmm. If you scroll and scroll all the way down to options A and B, you'll see binomial PDF and binomial CDF. Is everybody with me? Okay, binomial PDF is the one that gives me X equals. We're trying to find the probability that X equals. So can you guys choose binomial PDF? It's going to ask you for some things. So the first thing it asks for is trials. What should you put in?
20.
Okay, go ahead and put in your 20. The next thing it's asking for is probability. That's the probability of success for a single trial, which you can either type in 1 divided by 6 or put 0.167, whatever. It'll be close. And then your X value. Your X value is going to be the one we're trying to find. Okay? Okay. So, to give you kind of some perspective, are you with me that I'm not writing out this entire table? Right? But there is a table such as this one that goes all the way down to 0 and all the way up to 20. Is everybody okay? All right. What we just did to give you some perspective is we figured out that in this box, if I use that long formula, this would be 0.2022. Did you use 0.167? Yeah, I used 1/6, so it's just a rounding thing. I'm not super worried about it. Okay? Are we good? Okay. Next question. So the PDF gives you an individual box. Okay. So what if I ask you, what is the probability we roll at most 5 3s? What does at most mean? That means 5 is the biggest and everything less, yes? So that would be X is less than or equal to 5. So this is a CDF question. So you're going to put this into the binomial CDF. A reminder, second, bring up the distribution list and choose binomial CDF. I got 0.897 or 0.898 or pretty darn close to that. Okay? You guys. When I used the CDF, it did not tell me this box. It told me all of these. It told me that all of these was 0.898. So it gives me that box and everything lower than it. Is everybody good? All right, same context. So now if I ask you, what is the probability we roll 3 less than 8 times? Are you guys with me? Less than 8 is strictly less than. There's no equal to there.
So it would be like 7.9.
Now, binomial variables are discrete. Can you roll 7.9 times?
No, you have to roll 7 times.
So you say which ones are less than 8? Is everybody with me here? So if it just says less than 8, what we have to do is kind of make some sense out of that. We can say less than 8 times is really less than or equal to 7 times. And the reason I drew this table, even though it's a pain, is it can kind of help us start to see what we got going on here. I got 0.989. Really likely. Are we feeling okay? All right, so I'm just going to make it a little bit worse. Not a lot, just a little. You guys. This next one. Let us find the probability. At least 7. That'd be greater than or equal to 7.
So what we currently have, wouldn't it just be that answer we got last time, and then 1 subtracted by that?
Are you guys with me that this is greater than or equal to 7? Those are the outcomes. My calculator can't do greater than or equal to. So which ones am I subtracting?
6.
6 and below. So I got to do 1 minus the probability x is less than or equal to 6. You got to do 1 minus, not that minus 1. Or just recognize that the subtraction problem's flipped and it's the opposite. You should never, ever, ever get a negative probability. Probability is always in between 0 and 1. Is this feeling okay? Great. Can I make it ever so slightly more annoying? Just a little bit more annoying, not a lot of it. Okay? Suppose 40%, totally new setting, new context. Suppose 40% of statistics students will major in business. You take a random sample of 15 of them. What is the probability that more than 10 will be business majors? All right, you guys. Is this binomial? Before we use this binomial in the calculator, we want to think it through. Do we have a set number of trials? Yeah, it's now each trial is the randomly selected statistics student. Okay? And what is the probability that that statistics student is going to major in business? 0.4. Yep. And this is binomial, so we are going to say, what is the probability that x is bigger than 10? A water lid?
Yeah, like the lid to a screw top lid.
I don't have one.
Right here.
I had one this morning and then I recycled it down the hall.
What happened to his? Deflected with a student.
Probably. Okay. You guys. What do you think on this one?
The same idea as.
We're going to do 1 minus, right? If this part isn't coming naturally to you, do this. I promise you, you've got x, ... p of x. Okay. 9, 10, 11, 12. Okay. Which ones are we trying to find? Nope. Greater than 10, we're trying to find these ones. So we are subtracting these ones, which are less than or equal to 10. So, like, this is hard. Like, this is definitely one of those skills that students struggle with, okay? So up here, we had to bring it down by 1, but here we didn't. And here's kind of what happens. There's like a boundary point here, right? Like, we know we're subtracting something, and the question is, what's happening at that boundary point? Here, the boundary was 7. Am I including the 7 here? When I say greater than or equal to 7, am I including the 7? Yeah, because greater than or equal to has the 7 here, so I have to exclude it here. Whereas over here, my boundary point is 10. Am I including it here? No, so I have to include it here. It needs to be included exactly once. I think it is easiest, if you struggle with this, do this picture so you can see the where that upper boundary for that less than or equal to is. This is a pain. No question about it. This is the hardest part about binomial distributions. Plugging and chugging the calculator is not bad. It's the what are you plugging and chugging that is important. Okay. And then for that, the rest of that, it was 15.4. I got 0.009. Oh. Overall, I got 0.009. Everybody good? All right, just a little bit more on the top of the next page, and then we'll be done. I don't want to create this whole table and use that to find my mean and standard deviation because these are so predictable. There are equations. Okay. So, yesterday we talked about finding the mean and the standard deviation from the table, right? And then we talked about unusual values. In the same ones that are on your formula sheet that will give you the mean and the standard deviation of a binomial. Okay? So, the biggest piece is going to be recognizing this as binomial. These are the formulas I want to use. Okay. So, in this particular case, we take a random sample of 15 students, so we still have n equals 15, p equals 0.4. If I ask you what is the mean, you're going to say 15 times 0.4. This is equivalent to if you typed it in that typed in the whole table. This is a way better way, way faster way to get there. Okay? The standard deviation will be the square root of 15 times 0.4 times q is that probability of failure. And I got it to be 1.90. Everybody good? Okay. Lastly, would it be unusual? Just like binomials are a type of random variable. What did we say yesterday about unusual?
More than 2 standard
more than 2 standard deviations from the mean. So some of you do 6 minus 2 times 1.9. Some of you do 6 plus 2 times 1.9. So we can say, what is 2 standard deviations? 9.8? Okay. So would it be unusual to get 1 business major? Yeah. So 1 is unusual. What about 8? 14? Everybody good? Cool. Hey, real quick reminder. What's going on tomorrow? We're going to do the Poisson distribution. We'll probably have a little bit of time towards the end, I would think. But you've got homework due by midnight, Excel lab due by midnight.
The homework is what you gave us like a while ago, isn't it?
The homework is online.
Yeah.
And they're both due tomorrow by midnight. I'm available before school and all you get, like my availability is always there to help you with it if you're coming across questions you don't know how to do. Okay?